Good morning. My name is Stefania Cuoghi. The topic of my research is compensator design and sensors. My tutor is Professor Danasi and my co-tutor is Professor Rovati. My research has been focused on these three main areas: the design of lead lag and PAD types compensators, and the graphical constructions on the Nyquist plane of first and second order regulators. And finally, we put my attention on the power inverter control design on grid-connected photovoltaic systems. As regards my first research activity, let's look at the block diagram in the slide where GS is the plant to be controlled and the CS is the compensator to be designed. Design specification on the phase margins, gain margins, and crossover frequency are often imposed in order to obtain the desirable performance and the robustness of the control system. So the design problem formulated in order to meet this type of regulators can be satisfied using the inversion formula method. That is already used on automatic control courses, but only for first order lead and lag compensators. We found the relation to extend that method to second order lead lag and PAD compensators. A new graphical solution is also found, and that could be very useful both on industrial and educational environments. Well, I'm going to illustrate the method only in the case of lead lag regulators. In the slide, we can see the form of the compensators and the Bode and the Nyquist plots. Note that the Nyquist plot is a circle that depends only the gain gamma of the regulators. So we can define the controllable domain to the point B, the set of all the complex points that can be moved to point B by the regulators. And it is shown in gray in the picture. So, given a point B of the complex plane and chosen a point A belonging to the controllable domain to the point B, the set of all the lead lag compensator that move the point A to point B can be obtained using the parameter shown in the slide. Well, as we can see in the picture, variation on the freedom degree omega n modify the shape of the red loop transfer functions, but all of them pass on point B. So if the point B is on the unitary circles or is on the negative real axis, that property can be used to satisfy the gain margin or the phase margin at a given crossover frequency. The freedom degree can be used to satisfy another specification. So we found the closed form solutions and the graphical solutions of the design problems whose design specification are shown in the table. I'm going to illustrate the solution only in the case of the design problem C. So given the phase and the gain margins and gain crossover frequency specifications, the closed form solution can be obtained using the parameters shown in the slide, where x and y can be calculated using the inversion formula. The design specification completely defines the 3-point AP, BP, and BG, determining the black and the blue circles. So the intersections point of the blue circles with the green line, which denotes the transfer function of the plant, are the sets of all the points that can be moved to point BG by the freedom degree omega n. In the example, we have two acceptable solutions. Without entering into details, These are the closed-form solution and the graphical solution on the Nyquist and the Nichols planes of the design problem E. We also extended the method to the continuous and the discrete PID regulators. We found very similar relations for both time domain. And in particular, the discrete design can be also obtained by the continuous regulators using bilinear transformation with pre-warping. Well, as regards my second research activity, I wrote a relation on the mathematical and the geometrical properties of the first and second order regulators. Here I reported only some nice graphical constructions. That work could be very useful for a future research activity deals with cascade compensator design. While my third research activity deals with the power inverter control design. And we designed the power-oriented graph model of a grid-connected photovoltaic system architecture recently proposed in literature, and its prototype is shown in the photo. Well, we can directly see the correspondence between the different parts of the hardware structure and the POG model. The first section denotes the input panel and the filter, and the input filter. Then we have the DC-DC converter. This is a single-phase converter, and it's composed by an input full bridge connected to an active half bridge through an high-frequency transformer. Then there is the connection bus, and section 6.7 denotes the DC-DC converter, which is PWM controlled. And finally, there is the low-pass filter. These are the state space equations of the system. As regards the power management control scheme, we can see the hardware system in the part above and the control system in the part below. And in particular, the control is made by a microcontroller. The DC-DC control is based on a maximum power point tracking algorithm in order to transfer to the grid the maximum power flow provided by the panel. Well, as regards the control of the DC-AC converter, that is designed in order to transfer to the grid the power of the panel according to the European standard. And in particular, the modulation voltage is regulated in order to transfer zero reactive power to the grid and to maintain the bus voltage at a reference value. The feedback control loop elaborates the sense bus voltage and the sense grid and current voltage. And these are transformed into constant value by part transformations. In particular, we improve that part of the control by substituting two PI regulators with a function block which exactly calculates the output value on the base of the filter transfer function. And finally, the simulation results, compared with data found in literature, confirm the goodness of the model. Well, as regards my future works, we are going to apply the inversion formula method in order to satisfy other design specifications, and we will design a self-tuning procedure based on relay system suitable for industrial applications. And We also improve the photovoltaic system model and control. Finally, these are the papers that we wrote. Thank you for your attention.